All right, this is the second hour of Physics 1C for October 11th. So we're going to solve this problem that's related as an application of what we just learned. And what we have here is an 18 gauge copper wire. It has a cross-sectional area of 8.2 times 10 to the negative 7 meters squared. Wrote that down. It carries a current of 1.67 amps, I equal to 1.67 amps. And we want to find the electric field magnitude in the wire. We want to find the potential difference between 2 points in the wire that are 50 meters apart. So we're going to say that L is going to be equal to 50 meters for this part. And then part C, the resistance R of this length of wire. Okay. So given what we have information here, we also know that it's copper, which means that we can look up the resistivity for copper from the table above, right here. Copper has a resistivity of 1.72 times 10 to the minus 8. That's in units of ohms times meters. Okay, so the first question is to find E, and one of the equations that we have above tells us that the resistivity is equal to the electric field divided by the current density. And since we have current and we have area, should I draw a picture of this? Probably should. So here's our wire. It has a cross-sectional area A, has a length L, it carries current I, and we know that resistivity is electric field divided by J, which means that if I take J times rho, I'll get E. And that means that if I do J, which is I over A, so 1.67 amps divided by 8.2, that, and then we multiply by the resistivity over here, 1.72 that, then we should get the electric field. So it's 1.67 times 1.72 times 10 to the minus 8. Here, I'll just do this. This is so dumb for me to do that. Okay, so 1.67 times 1.72 times 10 to the minus 8. And then we divide by 8.2, 8.W, E minus 7. And we get 0.035. And we'll check the units here too. So 0.035. It should be in units of volts per meter or newtons per coulomb. Let's just check though. So checking the units. What we have here is, let's see, amps is coulombs over seconds. An ohm is a volt per amp. You can figure that one out because V equal to IR, which means R is volts over amps. So, or sorry, R, which has units of ohms, is volts over amps. Okay, so that's coulombs per second times ohms, which is volt per amp, times meters, and then we divide that by meters squared. So one of these cancels. A coulomb per second is the same thing as an amp, so that whole thing cancels. So you get volts over meters like that, which is good. So that's the size of the electric field in the wire, 0.035 volts per meter. Let's go on to part B. We now want to find, did anyone have any questions? Okay, part B, we want to find the potential difference between 2 points in the wire that are 50 meters apart. So if we want to find delta V, we're probably going to want to use that equation. We have I, but we don't have R. So let's find R. So actually what we're going to do is we're going to do part C first. So part C says to find the resistance, assuming that the length is 50 meters long. We know what the cross-sectional area is. We know rho. So resistance is rho times L divided by A. Right? Let's look this up over here. Yep, rho L over A. So if we take the resistivity of 1.72 times 10 to the minus 8 ohm meters, multiply by L over A, so L is 50 meters, and the cross-sectional area was 8.2 times 10 to the minus 7. That's meters squared. This will give us the value for the resistance. So it's basically the same thing we just did, 1.72 over this, same ratio, times 50 now instead of 1.67. So what I'm going to do is I'm going to take the last thing we did and just multiply by 50 instead of this. And I get about 1.05 ohms. That's going to be the resistance of our wire, and then we can use that to do part B, because then if we take I times R, that should be equal to delta V, which is what we want to find here for part B. So that's going to be 1.67 amps multiplied by 1.05 ohms. It's going to be pretty much, it's going to be 1.67 pretty much. But if we basically do this times 1.67, get 1.75. Volts. Pretty easy, right? It's almost like a completely different class at this point compared to what we were doing, earlier on. Just really simple equations. It's quite nice. It will, of course, get a little bit harder, but not by much. Okay, so the next thing we want to talk about is the temperature dependence of resistance. So let's do that. Accurate description, yeah. Yep. Okay, so if you've taken, who here has taken 1B? I know at least one person in this class is taking 1B right now, but who here's taken 1B? A few people have? Okay, cool. So one of the things you probably learned when you took Physics 1B is that anything that has temperature, anything that's hot, the molecules tend to vibrate a lot. And when they get hotter, they vibrate with bigger amplitudes. The molecules do. So what happens as a result of that is it actually increases the resistance of the substance. So pretty much what we can say is that as the temperature of a substance goes up, its resistance also goes up. And we can even plot it. It's a very simple kind of curve that if we plot resistance here on the y-axis and temperature here on the x-axis for what we call ohmic conductors, you get a very kind of straight line that goes up like this. That the resistance and temperature are just directly proportional to each other. And when you know you have a straight line like that, you can write an equation down like this. I'll write down what the equation says. It says rho as a function of temperature is equal to the value of the resistivity, a certain number that you know, plus alpha times the temperature change, where alpha is going to be the temperature coefficient of resistivity, which should be somewhere around here. Oh, did I not copy it over? Okay, maybe it's in the other slide. I thought that I copied it over. Click here. Oh no, I didn't do that. So I guess I'm gonna have to just pull it up from the book when we do it. Okay, my bad. Here we are. So alpha is a number that you're going to look up in the textbook. So just to show you that, it's this one, right? In the chapter that we're in, which is this chapter, talk about, nope. So resistance. Oh, wait. They're not in the book. Why did I think they were in the book? From table 25.2. This is 25.9. Oh, it's right here. There we go. These are the temperature coefficients. So they're just numbers. They have units of degrees Celsius inverse. Might as well show these pictures here since we're on the book anyway, so I don't have to draw them myself. I really don't know about this one right here. Because they show you this. Oh, okay. Never mind. All right, so there's three different things here. There's a metal, there's a semiconductor, and there's a superconductor, okay? A metal, the resistivity basically increases with increasing temperature. For a semiconductor, which is stuff like graphite and silicon, what else? Here, we can go to the that periodic table, actually. So do I still have it pulled up here? So it's like silicon, germanium, maybe arsenic too, are semiconductors. There's all kinds of different materials that can be semiconductors. The point is that the thing that differentiates them is that for metals, the resistivity increases with temperature. Semiconductors, the resistivity decreases, which is quite nice. And there's something called a superconductor, which is a material that below a certain critical temperature, the resistance actually drops to zero. And this is a type of material that is extremely popular for kind of modern research, is looking for objects that can have a superconductivity state at a relatively high temperature. Right here, they're talking about how by 1987, an oxide of yttrium, copper, and barium was found that had a critical temperature of about 77 Kelvin. And that's... it's well above the 77 Kelvin boiling temperature of liquid hydrogen, which is a refrigerant that's both inexpensive and safe, which is the point that, like, if you can, at 77 Kelvin, you can easily show in a lab that it's a superconductor without having a really powerful refrigerating system. Nowadays, we're looking for temperature of a superconductor to be closer to room temperature because superconductivity has a lot of advantages. So let's go back. We'll talk about that in a second, but let's look at this equation that we have here, and let's talk about why that would be the case. Since the resistance increases with temperature, you can see that this might cause some kind of a problem. Like, let's say you have some electronics and you need to have a certain amount of current flowing through them, but then the electronics start to get hot. What's going to happen to the current flow if the resistance goes up? What's going to happen to the current flow through your system if the temperature... So if the temperature goes up, the resistance is going to go up, and the current flow is going to go down, right? So if you have certain devices inside your system, like, I don't know, your CPU or something that requires a certain amount of current to flow, then if it gets too hot, it might not work anymore, and the system might crash or something like that, right? So you can imagine that if instead of constructing your computer or whatever device out of a material that has this problem, if you could somehow construct it out of wires that are superconductors, then this wouldn't be a problem. You could keep the current flowing, and not only that, you'd have very little loss of energy to the system, because if there's no resistivity, that means that the temperature of the conductor itself isn't actually going to get hot, right? Does that make sense? And that's really powerful, because dumping heat out of systems is a really big problem. There's other things you can do with superconductors, but another thing I'm going to say is that because resistivity, so resistance is basically just equal to rho times L over A, you can also say that resistance as a function of temperature has exactly the same form, like this. The alpha quantity is exactly the same. a superconductor computer exists? No, I don't think, not yet. We're still searching for materials that we can use. Superconductors are also really popular because they can produce a phenomenon that looks like levitation, where you can take a superconductor and you can place it above a magnet, and it will basically just be locked in place. So there's a lot of ideas that you could use superconducting rails to levitate like a maglev train and have very, very little friction going on. Okay, let's look at an application just so we can just understand how this works. When we go into the lab, I'll show you a proof that this is true, that resistance and temperature work like this. We have a demo where we have a light bulb that's kind of like open to the air, and what we can do is I can turn it on and then I can blow on the light bulb to cool it down basically, and the light bulb gets brighter. So I'll show that to you all. Those of you that are coming this week for the lab, I'll try to, if you remind me, I will show you that demo, which is pretty cool. Okay, suppose the resistance of a copper wire is 1.05 ohms at 20 degrees Celsius. So we have the resistance at 20 degrees Celsius is 1.05 ohms, right? We also have the initial temperature then. That's going to be 20 degrees Celsius. Find the resistance at 0 degrees Celsius and at 100 degrees Celsius. And we're going to have the alpha value for copper right here. Alpha equal to 0.00393 degrees Celsius to the negative 1. So, pretty easy problem. We want to find the resistance at 0 degrees Celsius. Let's do that one first. This is going to be equal to that same initial, so this is our equation. So I'm just going to start plugging things in immediately. This is a straight plug and chug kind of problem. So 1.5 ohms is the resistance at our initial kind of temperature, plus alpha, which is 0.00393, multiplied by the temperature change. So that's going to be, the temperature we care about here is going to be the temperature that shows up in here. So 0 degrees Celsius, so 0 minus 20. And then this should give us a value that is less than 1.05. Okay, so it's 1. So we get 0.967, and the other calculation we're going to be doing is for 100 degrees. So the only thing that's going to change is right here where there was a 0, there's now going to be 100. So those are our two values, 0.967 for this one, and then 1.38. And you can do the same calculation. I'm not going to do it because it is super simple, obviously. Plug in 100 and set a 0 and you get that. So those are the two answers we get. Pretty easy. Anyone have any questions? Do you want to see what a superconducting magnet levitating thing looks like? Do y'all want to see that? Does that sound interesting to you? Okay. I don't want to use. I would love to watch this whole video. It's wonderful, but I kind of want to keep things moving, so to speak. So we'll watch just a very small amount of it. I have to switch windows so that you can hear it. I don't think you have to be able to hear it, but okay. I don't hear anything. Do y'all hear anything? You do? Oh, you hear something because it's probably playing through my television. Okay, that's fine. As long as you guys can hear it, that's fine. All right, so we're going to kind of zip through this. I apologize. The beginning, he kind of fumbles with it anyway. He's going to talk about superconductors. He's going to talk about magnetic fields. We haven't talked about magnetic fields, obviously, yet, even though we will in this class. He's talked about resistance. Resistance produces heat. superconductivity conditions, blah, blah, blah. You're more than welcome to watch this yourself. Maybe later on, after we talked about magnetic fields, we might talk about this again. Right, but then eventually he's going to do a demo. Okay. There it is. Okay, it starts right here. Now we'll watch this part from here on. Is it in slow-mo? It is in slow-mo. Okay. There you go. There's the levitation. So the thing on the bottom is a magnet, and then the material is a disc that is the superconductor, and it's just wrapped in foil. So, isn't that cool? You can turn it upside down and it still doesn't fall off. Oh, this thing is so weird. Alright. So this is the part that's really cool, I think. So he has to keep cooling it off. That's what the little container there is. It's full of liquid nitrogen. So 2 different types of magnets. This magnet is a donut. If it gets too hot, it loses the superconducting state, which is what causes it to fall. All right, so now he's going to talk about some stuff, which is definitely interesting. Definitely interesting. Now he actually shows you how thin it is. Look how thin this thing is. Half a micron. A micron is one micrometer. Look at that thing. It's so tiny. He's saying it can hold 70,000 times its weight. Okay, so now we get to the good part, where he actually uses this track right here. So he has, yeah, here we go. This is what we want to watch. Isn't that amazing? Yeah, it seems like magic, doesn't it? It's pretty cool. All right, he's going to talk about some stuff now, but not hard to find this TED Talk. It's a TED Talk about superconductors. You can just Google what I do. I Googled superconductor TED, and it came up. It's like first result. Very easy to find. You can find other videos. You're going to see applications of this in your life for sure. 100%. Yeah, definitely. It's just... if you follow the news, you'll see news articles where they say, "Oh, we found a," like just recently there was an article where they said they found a room temperature superconductor, and the way they did it was they had this metal that was subjected to really, really high pressure, if I remember correctly, and they could produce a superconducting state at that really high pressure. So we're learning new things every day, and the progress and march of science goes on. Okay, so the next thing to talk about is, we're getting through things so much faster than I thought I would, is EMF. That's the next topic, electromotive force. So it's usually written as a lowercase, EMF, and it stands for electromotive force. It's not actually a force. It's more like voltage. Oh, you know what? You probably can't see what I'm writing now because it's still doing the other thing, so I have to switch back. My bad. Sorry. Screen. Change windows. OBS. Go live. Okay, you can see what I'm writing now, right? So as I was saying, EMF. It's good now, right? The stream's okay now? Okay. So EMF stands for electromotive force. It's not a force. It's actually kind of like more like voltage, basically. But it's called a force for historical reasons, okay? The units are volts. Okay? So it's most closely related to voltage, although it's not exactly the same thing as voltage. So in order to, I don't know, I guess envision, what this is, we can imagine that a battery can be kind of thought of as something like this here. Zoom in just a little bit. Okay. So not just a battery, but really any EMF source, okay? So here's our picture of a source of EMF, okay? A source of EMF. A source of EMF is going to be something that can provide, well, EMF or provide electricity, really. Okay? And examples of EMF sources would be things like, obviously, a battery. The things that you used in the labs this week were just called power supplies. Very uninteresting name. There's also things like solar panels. What else? How else do we get electricity? So an EMF source, you could replace that with the source of electricity. How else do we produce electricity other than things like this? How else do we produce electricity? Okay, so nuclear power, turbines, sure. So turbines, wind, nuclear can all be kind of summarized as generators. So clumped within generators would be things like wind power, hydropower, nuclear power as well operates off the same concept, and also fossil fuel power. People are always saying that, we want to kind of switch over to renewable energy, but I don't know if you knew that fossil fuels and wind and hydro produce their energy in exactly the same way. They just involve, basically, you need to have a turbine that moves in a circle, and then you attach to that some coils, you put it all around a magnet, and that's how you generate electricity. We'll learn all about how generators work later on, but generators are at the core of how wind, hydro, nuclear, fossil fuel. By thermo, you mean what? Maybe like geothermal? Is that what you're thinking of? Or be another one here? Okay. What else is there? Batteries, power supplies, solar panels, generators. How else do we get electricity? A lightning rod, you can imagine you could maybe use to store electricity, sure. But it can't really be a source. I guess it could in a way. All right, I don't immediately think of any other ones, but if any of you do, let me know. Put it in the chat. Okay, so EMF source in general is what we're talking about here, and it's represented by this box here, okay? Now, the idea is that you're going to have a positive terminal over here. You're going to have a negative terminal down here. And then within the EMF source, there's going to have to be some type of non-electrostatic force that tends to move charges to a higher potential. Yes, Stefan, that's nuclear, basically, I think. It's included in that kind of idea. You use the heat produced in nuclear reactions to boil water, which you then use to drive turbines, basically, the idea. Okay, so definitely a good point, though. Okay, so there's a non-electrostatic force that tends to move the charges to a higher potential. Now, what that non-electrostatic force is, okay, is going to depend on what the type of system that you're talking about is. In the case of a battery, the non-electrostatic force is some type of a chemical reaction that tends to push charges in a certain direction. I don't know what it would be in the case of a power supply. In the case of solar panels, the non-electrostatic force is the force of the light hitting the electrons in your circuit. In the generators, it's a magnetic force that is doing this. But the idea is that there is a non-electrostatic force within the battery that pushes charges up to a higher potential. You'll notice that within the battery itself, because this is a positive terminal and this is the negative terminal, the electric field produced by those actually has to point downwards. But the goal of a battery is basically to lift charges from one point here up to here, giving them some amount of energy so that they can then circulate around a circuit. So let's draw a circuit now. So in a circuit, you're going to have your battery with its positive side and its negative side. The battery is going to be connected up to something. So let's say, for example, that we connect our battery up to a light bulb. So here's our light bulb. Now, what we're going to do is we're going to label the battery with this symbol E. EMF is usually symbolized with this curly E right here, is what you're going to see in your book. Okay. Now, that's our EMF source, right? And it's connected up to, as you can see here, a light bulb. Right? So what happens? So let's look at a single charge as it moves around this circuit. So imagine you have a positive charge right here. Okay? What the battery does is it takes this positive charge and it lifts it to this location here. All right? And it does that basically against the electric field. Inside of the battery, the electric field's pointing the opposite direction. So by pushing this object up to here, it now has energy. We can say that it has potential energy. And because it has potential energy, and because it's at the higher voltage point, like for example, this point right here, we could say maybe is 10 volts or something like that. And this point right here, we could say is 0 volts. Then the fact that this charge has energy means it's naturally going to want to flow around the circuit in this direction here. It'll eventually flow through the light bulb, causing it to brighten up. It'll flow back to here, and eventually it'll get right back to where it started. And then what the battery does is it lifts that charge up here again, giving it energy, and then it is able to go around in this path. How does the battery do that? It does it through a chemical process. I have a video that I shared on on Canvas that kind of goes into a lot more detail about how a battery works. I'm not going to go into the detail, but just say that there's a chemical reaction that occurs here that pulls the charges from the bottom up to the top and then causes them to flow around the circuit like this. And when that's happening, we say there's a current flowing through the circuit, and so on and so forth. There's a pretty good analogy for what's happening in an electrical circuit like this. And the analogy that I like to use is like a water pump. So I'll just draw it kind of side by side right here. So imagine that I have a fountain, okay? And the way my fountain's constructed is that I've got a pool of water down here. And then I have a tube that comes out of the water here. And then this tube continues like this into kind of like a faucet right here. So here's this tube. And then within the tube itself, let's say like right here, I have a water pump. So I'll just draw it like this. This is my water pump. Because as you know, water will not naturally climb up hills, but if you can attach some type of a pump that's either driven by your hands or by electricity possibly, then the water will start to flow up in this direction here. So you're going to get water that's going to flow up through the tube. It'll flow into here. And now, this water has potential energy, right? And as long as the pipe has a way for the water to get out, then due to the water pressure in the pipe, it's eventually going to fall out this side over here. And there'll be water that kind of just, there's going to be a stream of water that's going to be flowing down this way. Back into the original vessel. So now we have a flow of water that's continuous, right? There's a kind of a current flow in a way from the water that goes all the way through this process. And then if you think about an individual droplet of water, what happens? Well, it starts down here, gets lifted up to here by the pump. It now has potential energy, so it naturally just kind of flows this way. You don't have to put any more energy into it here because it's automatically going to flow out the other side. And then it falls back down to the bottom where, in order to continue its path again, the water pump has to give it energy and lift it back up to here, right? And what's going on inside of the water pump? Well, inside the water pump, we know that the gravitational field points down like this, just like inside of our battery, the electric field points up like this. But if you can get something to the top of that electric field, well, now it's going to flow around in the same sense that the water will flow around as well. One thing that is a little bit confusing about this, but this is true and it's something to keep in mind, is that even though the electric field inside of the battery points down, the electric field in the wire points this way. Okay? It points in the same direction as the current. Okay? Okay. So, does the analogy make sense? Does it help to understand what's happening inside of what the battery is doing effectively? It's just pumping charges from low energy to high energy. Once they have energy, they can do the rest. So the battery just has to get it from here to here, and then the charge is going to do the rest. Okay. So that's what we call an EMF source. And how are we doing on time? 3:05. So we're doing fine. The next thing we want to do is we want to talk about the fact that the battery tends to have resistance inside of it. So there's an equation that I pulled up over here. So I'm going to write this in a slightly different way, but I put it here because you're going to need to see this. So when we talk about a battery, the battery itself tends to have some resistance. So one thing you're going to see drawn in some of your problems is that inside of your circuits, you're going to see a battery and it's going to look something like this. Remember that this is the plus side and the minus side of a battery, but there's going to be another little symbol right here. Oh, I didn't even tell you all. This is the symbol for a resistor. Oh, I guess that's why I had this other piece right here that I might as well include as well. Let's grab both of these because this is what we're going to need to... Okay, so here's our circuit diagram symbols. Right there. So our symbol for a resistor is this jagged line. Symbol for our EMF source is going to be this. Oh, there's also a picture in here as well. But you're also going to see symbols like this that have the EMF for the battery is going to be labeled by E, and then the resistance here is going to be labeled R. And what this equation over here states is that if I look between... well, let me... click. There we go. If I look between this point and this point right here, and I call this point... gotta think about how they've written this. I think this would be A and this would be B, the way that this is written. Just thinking for a second to make sure that I think that, yeah, that's true. The way they have this written here is to say that this, between these 2 points, they call that the potential difference of point A relative to point B. I would just call it delta V, because that's just easier for me, but either way. And this is the equation that they have written down here, that the potential difference between these 2 points is going to be equal to E minus I times little r. So little r is going to be the internal resistance of the source. So our battery is going to have its own internal resistance. And yeah, so that's an equation that relates the EMF of the battery to the actual output voltage. So for example, if the battery had an internal resistance that was equal to, let's say 10 ohms. That would be a large number, but that's okay. And there was a current that flowed through it, I, that was equal to 0.1 amps. And I told you that the EMF of the source was actually supposed to be measured to be, let's say it was a 12-volt battery, okay? If you then go and actually get a multimeter and you measure the voltage of between these 2 points, that you'd find that the answer would not be 12 volts. And instead what it would read would be 12 volts minus 0.1 amps times the internal resistance of 10 ohms. So instead what you'd be reading when you hooked up a multimeter would just be, looks like 11 volts, right? Does that make sense? So let's do a problem. Okay, there's enough room here, right? Okay. It says there's a previous problem to this one, but we're jumping ahead. We add a 4 ohm resistor to the battery in a conceptual whatever, forming a complete circuit. What are the voltmeter and ammeter readings now? Okay, so here's our circuit. We have a ideal EMF source, or sorry, we have an EMF source that has an EMF of 12 volts, an internal resistance of 2 ohms, and it's connected up to, so there's our battery, it's connected up to a resistor right here, and then in series with the resistor is an ammeter used to measure current, and then there's also a voltmeter, V, that's attached in parallel to the battery here. And we have to calculate what the readings on the voltmeter are and the ammeter are going to be. Okay? Yeah, definitely, somewhere to E3. So how do we do that? Well, first of all, we can measure the potential difference in 2 different ways. Notice that there's a current flowing through this circuit here. The current is flowing in this direction. You can see it flows out this way, back through here, right? And the same current is going to be flowing through this whole circuit here. We're going to assume that the voltmeter has a very large amount of resistance, which means it's not going to affect the resistance of the system. Okay, so what do we do? Well, what I would say is that if I want to measure the potential difference between points A and B, we already have one equation that tells us that potential difference should be equal to E minus I times little r, where little r is the internal resistance of the battery, shown here. But point B and point B prime are basically the same, and point A and point A prime are basically the same. So this same potential difference should be equal to the potential difference drop across this resistor right here, which is going to be I times R. So basically all I've done is I've used the equation that we just saw right here, combined with our other equation, which is delta V is equal to I times R. And we're just going to use these to solve for one of the unknowns, which in this case is I. So let's solve for I. Before I do that, does this process make sense? Okay. So the EMF in this case was 12 volts. We're dividing by big R plus little r, so little r was 2 ohms plus big R. Oh, whoops. And then big R was 4 ohms, I think. So we end up getting 12 divided by 6. So we get 2 amps. We could then use this current and say we know delta V from before was equal to I times R. So if we just take 2 amps and we multiply by big R, which was 4, then we get that the potential difference delta V, which is going to be read out by the voltmeter, is going to be 8 volts. Pretty tricky stuff. Anyone have any questions? Okay, one other thing to talk about is power. Then we'll take a break. So this can almost be figured out just by thinking about the way that the units work. Okay, so say that I have, same thing that we've been talking about. I've got a battery. It's connected up to a resistor, R, so that there's current I flowing through my circuit, and I have a potential difference, delta V, here coming from my source. All right. We know that the units of current, right, are coulombs per second, right? The units of voltage, delta V, are joules per coulomb, right? What are the units of power? What are the units of power? Watts. And 1 watt is 1 joule per second, right? So I've got coulombs per second and I've got joules per coulomb. If I take coulombs per second and I multiply by joules per coulomb, I'm going to get coulombs per second. Or sorry, I'm going to get joules per second, right? So what's coulombs per second? That's I. What's joules per coulomb? That's delta V. And that's how you get power. You take current and you multiply by voltage. You can figure out how much power things that you own consume. I wonder if this one shows. It's hard to read. Well, it's really hard to read. Most things that plug into the wall will have numbers written on them. Like if you look at your phone charger, it might say something like 1 volt at 0.5 amps, for example. Different chargers are going to say different things, but let's say that you look at your cell phone charger and you notice on the back of it that it says that it's rated for a current of like 0.5 amps, and then it says at maybe like 12 volts or something like that. Well, that means that if you multiply those two numbers together, you get a power that would be equal to 6 watts, right? 6 watts. So if you have a charger and it says this on the outside, that means that it uses 6 joules per second. And you can even figure out stuff like, what does it cost to run, to power up my device over the night? And the answer is not going to be very much. Let's say you plug it in for 6 hours, okay? So let's say you use it for 6 hours. You could calculate exactly how much energy you use by taking power times time. So if you take 6 watts and you multiply by, well, it's going to have to be 6 hours multiplied by 3,600 seconds per hour. You could figure out exactly how much energy you use. Oops, scroll down so that doesn't get cut off. So how much would it be? That would be 6 times 6 times 3600, right? You get 1.129600, we'll call it 130,000. This will be 130,000 joules. But your energy company doesn't actually charge you for the amount of joules you use, do they? They don't charge you by the joule, do they? They charge you by something else, which is equivalent to, you could convert to joules if you want to. When you pay for your energy bill, maybe some of you never look at it probably, or maybe you don't pay for it at all. What do you usually pay for? Kilowatt hours, that's right. So if you want to convert the amount of energy you use in kilowatt hours, then all you have to do is to convert 6 watts into kilowatts, which would be 0.006 kilowatts, and then just multiply by the number of hours, which is 6 hours. So now what we're going to get is 0.036 kilowatt hours, right? And now you can figure out how much does that actually cost. Well, the price usually of energy depends on where you live and stuff like that. It's usually something like, let's say, 15 cents or $0.15 per kilowatt hour. So you can answer the question, how much does that actually cost to charge your phone in this particular case? And the answer would be, take this number and multiply by this number. So you would get 0.036 times 0.15 cents. It's like half of a penny is how much it would cost. The cost would be half of a penny. So not very much. Of course, if you change the thing that you're using, so we said it was using a power rating of 6 watts, right? If the thing you're using uses a lot more watts, like for example a light bulb, old incandescent light bulbs use energy of like 100 watts, right? So you'd have, roughly like 50 times as much, which means if you leave the light on for 6 hours, it might cost like, half $1 or something like that. Why can't you use the same charger in other countries? Is it the voltages that different countries use? Yeah, other countries have a different amount of voltage coming out of the wall, but you can use a converter, obviously, to convert. Yeah, we use 120 volts in America. In other places in the world, they use 220 or 240 volts. So you need to have... inside of a device that you plug into the wall, it naturally converts from the 120 volts that come out of the wall into something else, like maybe 12 volts, for example. All right, we should take a break, though. Right? Yeah, we should take a break. All right, let's take a break until 3:28 p.m.